Today we'll solve some problems related to asymptotic analysis. So we will be given some function and we will be given some bound in the big O notation. We have to either show that the function is bounded by the big O expression, or we have to show that it's not bounded. So the way we go about doing this is by using this definition. First of all, I would like to emphasize that I am looking for more of an intuitive understanding of what is going on rather than mathematical rigor. But I'll show you several examples that have been given in the workshop sheet, and we'll work out how to solve those problems. So this is the definition of complexity analysis or bounding by big O. You can see here that fn is order of gn. Fn is a function and it is order of gn. That means it is bounded from above by gn. If there is a constant c greater than 0 and an integer n0 greater than 1, such that for all n greater than equal to n0, f of n is less than equal to c times g of n. This definition I have explained several times in the lectures, so if you are unfamiliar, I would encourage you to have a look at the lecture recordings. But what I'll do today is to start from this definition and show how we can solve different problems. So the first problem we'll solve is we have to show that log of 3n square is order of log n. So while solving problems like this, we'll either show the statement holds or we'll show there is a contradiction. So what is the statement that we are trying to show here? We are trying to show that log of 3n square is less than equal to c times log of n. So if indeed it is true, then the claim that log of 3n square is order of log n is true. Otherwise, there will be a contradiction and we will infer that the claim is not true. So how to go about this? This is equivalent. The left hand side is equivalent to, if you remember the rules of logarithm, log of AB is log of A plus log of B. So we can write this as log of 3 plus log of n square, because just like A times B, 3 times n square was the original argument. So we have to show this is less than equal to c log of n. This implies that we can take out this factor log of 3 from both sides, because in an inequality we can subtract the same thing from both sides and the inequality still holds. So we can write log of n square less than equal to c log of n. Moreover, if we subtract from both sides, we can adjust the constant for this inequality to hold. Okay, so this is the situation right now. And if you remember another rule of logarithm, log of n square can be written as 2 times log n, which is less than equal to c log n. In other words, finally we have to show that log n is less than equal to c by 2 log n. Now we have the freedom to choose the constant c. So if we choose the constant c as greater than or equal to 2, then this inequality of course holds, because if we choose c exactly as 2, then log of n is less than equal to log of n. Yes, that is correct, because log of n is equal to log of n. If we choose c greater than 2, then of course log of n will be less than equal to that number here times log of n. So in other words, we have proven that log of 3n square is indeed order of n. Okay, so we go to the next problem. Problem number 2 is we have to show that 2 to the power n plus 1 log of n square is order of or big O of 2 power n log n. Again, we write the expression like that we have to show 2 power n plus 1 log of n square is less than equal to c times 2 power n log of n. So here this expression is what is important for us now. This expression here is important to look at. Now what we can do is, since n is greater than 0, then we can cancel out or we can eliminate terms from both sides. Before that, perhaps it's better to simplify the expression a bit more. So this can be written as 2 power n plus 1 is nothing but 2 power n times 2. This is the rule of exponents, and log of n square can be written as 2 times log n, law of logarithm. This we have to prove c times 2 power n log n. Now we can see that we can get rid of this term from both sides. This term cancels out this term, and also log of n cancels out log of n. So what we have after this cancelling out terms, we have simply this situation. This implies that 2 power 2 times 2 is 2 power 3 less than equal to c. Is there a constant c that satisfies this? Of course there is a constant c. If we choose c as greater than equal to 8, then it's indeed true that 2 power 3, which is 8, less than equal to c. So in other words, we have proven our original claim. So let's go to the third one. I was numbering 1 and 2, but actual numbering in the workshop sheet is ABC, so I'm using it here. We have to show that n factorial is order n power n. How do we show that? We write again the same expression. N factorial is n into n minus 1 into up to 1, which is less than equal to c times n power n. Now you can notice here that this thing here, the left hand side, has n terms. This left hand side has n terms, and only n minus 1 n's. In other words, if I multiply all the things here, I'll get something like n power n minus 1, some other factors, and which will be added, subtracted, etc. That is less than equal to, I am not writing the entire thing, because that what are those other factors will depend on what factorial you are considering. So what is important for us to note is what is the highest degree, which is n power n minus 1. As we know from the lecture, that is the term that is going to dominate. So in fact, we can omit all the other terms and live with this one. So this one, then what you are getting, if you eliminate or cancel out n power n minus 1 from both sides, you are getting 1 less than equal to Cn.